All right, let's get started. First rule of the semester, if you want to bring coffee, that's fine. 8 o'clock in the morning, mechanics and materials, I understand, so it's okay. Welcome back. I hope that your summer was a good one. I hope you got some relaxation, and I hope you're ready to get the semester kick-started. So welcome to Mechanics of Deformable Bodies. I think I've had a few of you in some classes before. I recognize some faces from yesterday from structural analysis. I think maybe I've had a number of you for Engineering 103. I taught that last time in fall 2016, and I recognize some of you from computations. But if you've never had me for a course, if you don't know who I am, I'm Dr. Michelson, going to be your instructor this semester, and I'm happy to have you here. And this is probably one of the most enjoyable classes that I get to teach. That I think you'll find throughout the semester that what we learn in this class is a very, very applicable science, not only to civil engineers, but mechanical engineers. And the stuff that we learn in here is stuff that you're going to be using throughout your careers. So this is a really exciting class. I know it's 8 o'clock in the morning, but I think you'll learn some pretty cool stuff today. I'm going to go ahead and pass out a hard copy of the syllabus. To be honest with you, this is probably the last hard copy thing that I distribute at all this semester, because I use Blackboard pretty heavily, and I'm going to show you that here in a second. But we'll get into that as we get things going. Okay, so there's 5. 1, 2, 3, 4, 5. Okay, there you go. All right. So I know it says here on my syllabus that office hours are to be determined, but I've pretty much already figured that out, so I've got that here. My office hours are going to be Mondays and Wednesdays from 1 to 3, and Tuesdays, Thursdays from 10 to 12. But I'm usually a pretty easy guy to get on and whatnot. If you don't or if this doesn't work, or if you need to see me about something, if I'm not around, send me an email, and I'll make sure to be here. I'm usually a pretty accessible guy. I don't have a homework for you today, and we'll look at the schedule here in a little bit. That homework's to be assigned Thursday, so you can relax there. I'm not a professor that gives homework every day. There's only a few homework assignments in this course. They're bigger, but there's less of them. But I only assign them at particular points in the lecture. But we'll get into that here in a little bit. Today, what I want to do is I want to talk about just an overview of the class, the course operation, how we're going to operate things. And since we only meet 2 days a week, I am actually going to get started talking about materials. So I want to talk about the most fundamental concept that we're going to be discussing this entire semester, and that's the concept of stress. But we'll get into that as we get things moving forward. So let's just go ahead and get into some things. First off, let's talk about the course operation, because I know on day one, it's something that you're always concerned about. So first off, let's talk about the grading. So I do have a very light component of the grade related to attendance. It's just a motivation to make sure that you're here. Speaking of attendance, I've got a sign-in sheet. I'm going to go ahead and start to pass that around. To sign in. I'll try to do that every morning. There might be a morning or two I forget. Just somebody remind me. Homework. This is one of those courses where really the best way to learn the material is to do it. So homework is a pretty significant component of the grade. As for the exams, I have 3 exams in the class. The final is worth a little bit more, not because I think that the final should be worth more, but it's because the way that this course goes, there's sort of a natural way that the topics should be sliced off in the exams, and exam 3 just ends up having a little bit more on it. So since you got to do a little bit more studying and a little bit more preparation, I figure I ought to give you more credit for that. So exam 3 is worth a little bit more. Now, let's talk a little bit about the textbook, and I'll just sort of say my textbook policy in general. By and large, the homework problems that I'll assign come out of the book. Okay, so I have really 2 messages I'd like to get across. The first is in regards to homework. Okay, I'm going to give you a homework assignment on Thursday, and it's going to be due not the following Tuesday, but the Tuesday after, so you get kind of like a week and a half on it. On that Tuesday at 8 o'clock in the morning, as long as I get a completed assignment turned into me, that's all I care about. Okay? So what I'm getting at is if you want to rent a book, or rent a book, you want to do a digital edition of the book, if you and your friends want to chip in and buy a book, as long as I get the homework turned in, that's all I care about. Because I know textbooks are expensive, and if you want to try and save some money and whatnot, that's on you. I'm completely fine with whatever you decide to do. That's my first message. That's in terms of course operation, like, do I have to buy a book? You have to turn the homework in. That's, I'll say that, okay? My second message I'd like to get across with the book is this, okay? I do think you should have one, okay? But I am not terribly concerned that you get this one, okay? You can get an older edition of the book if you would like. You can get another book. I mean, heck, you could probably go on eBay and find older copies of this book for $5 or $10 or something like that. I mean, a lot of the stuff that we're going to be talking about in here is based off of things that haven't really changed since the apple fell on Newton's head. So, you know, having this brand new edition of the book is not totally necessary to understand the concept. I do think you should have one, though. Look, y'all are engineering students, and I understand the motivation as an engineering student to get rid of your history book as soon as you use it. Like, I get that. Okay? You're not going to use that throughout your career. But this is a science that you will use. I promise you, this is probably one of the most critical sciences that you will use throughout your engineering career. So having a reference, I think, is a good idea. I'm not saying it has to be this one, but as long as you get the homework done for course operation, that's fine. So you totally on you. So everybody okay with that? Okay. All right. Now let's talk about attendance. So like I said, I'm going to pass an attendance sheet around every day. And it's pretty straightforward. I'm just going to take the total number of signatures, divide by the total number of days, and that's your attendance grade. Pretty straightforward. I'll keep that up to date on Blackboard. I'll try and update it maybe like once a week or so. I'm definitely probably not going to enter the attendance grades this week in case I've got some students that add the class or drop the class or what have you. I'll give the first week, you know, a little bit of buffer for everybody to adjust the schedule. But after the first week, I'll try and make sure the attendance grades are updated pretty regularly. Let's talk about lecture itself. So I record all of my lectures, okay? I have a link on Blackboard, which I'm going to show you here in a sec, that shoots you straight to a YouTube playlist. And every lecture I will add to that YouTube playlist, so you will be able to review that to your heart's content. I also, when I do problems in class, when I do example problems, I use the screen, like I use the little pen with the smart podium. So when you watch the videos, you can see the problems being done in real time. And the students, every time I've done this, the students seem to really like that, so I'm going to keep on with that. Like I said, I use Blackboard pretty regularly. I mean, it's not regular, it's pretty heavily in this class. All your grades will be posted on there, all the lecture notes, assignments, everything. So I do that because all you need is one login, one username and password, and you can access everything you need for this class. So I do that on purpose. So I would just make sure that you check that pretty regularly. I'll make sure and have stuff posted on there pretty often. Let's talk about homework. So I'm not that professor who looks as, oh, it's Thursday, I haven't given you all homework yet, I need to assign something. I don't do that, okay? There's a planned number of homework assignments in this class, and what I do is this. So first off, I don't assign homework assignments when you're not ready for them. Like, I won't say, okay, I'm going to give you this homework on torsion. We're not going to talk about torsion until next week, the way it's due next week. Like, I'm not going to do that to you, okay? I usually assign the homework assignment at least after the topic has been discussed or when we're right in the middle of it, so that by the time you get the homework, you'll be equipped to do it. I'm not going to give you a homework assignment that you're not ready for, okay? I usually give you about, like, the minimum time I usually give you is a week, but usually I'll give you like a week and a half. I have, I believe, 8 homework assignments planned for this course. So the homework assignments in here, I don't do as many of them, but again, they're a little bit longer, but I also give you more time. So I think it's a little less stuff that, you know, organizationally that you have to deal with. But, you know, on the flip side, the homeworks are a little bigger. It's not like every week it's a couple problems. It might be every 2 weeks there's 4 to 5 problems. So just be aware of that. In terms of my format, I like there to be a cover sheet on the homework assignments. If you want to print off the actual assignment and just put your name on it, that's fine too, to act as a cover sheet. The syllabus has, you know, specifics on what needs to go on it, and I'll remind you when homework time gets around. But in terms of format, I'm pretty easy to get along with. Just make sure that you use quad paper like you can use graph paper or engineering paper, but that's what I mean, just some sort of graph paper. If you have issues with your handwriting, the only thing I ask is just please try and keep your handwriting as neat as possible. And this course, there's a tendency to have some figures and some diagrams and whatnot on your homeworks. So if necessary, use a straight edge. And every single person in this room should have a straight edge on them because, I mean, look, here's a straight edge. So, I mean, there's really no excuse for that. So just make sure that, if there's any, elaborate diagrams that you're drawing them neatly, okay? Let's talk about the exams. So there are 3 exams in the class. One of them will be during finals week, and there's 2 that's during the lecture. Now, I want to explain this bullet point. The exams in this course are not intended to be comprehensive. And I mentioned this instructional analysis yesterday for those of you that are in there. But for this course, it's a little easier to parse out the different topics. What I mean by that is this. Exam 1 is going to be, for instance, on fundamentals of stress and strain, and then it's going to be on axial loads and torsion, okay? And that's it. When exam 2 comes around, I'm not going to test you on those topics. They're not intended to be comprehensive. But, for instance, like today we're going to talk about stress. You're going to see stress on every homework assignment and pretty much every lecture this entire semester. So there are going to be some concepts here and there that bleed over from exam to exam. But I'm not intending them to be comprehensive. I'm not a comprehensive exam guy. I like to examine you on these topics and then move on. On the exams, I let you bring a calculator and I let you bring a formula sheet, 8.5 by 11, front and back. You can put whatever you want on it. Formulas, procedures, equations, what have you. The only thing I don't let you put on the formula sheets are worked out examples. That's not for my benefit or me trying to say, oh, you can't do that because I'm the professor and I say so. It's really more for your benefit because, and I mentioned this in instructional analysis yesterday, but I said, let's say you've got a test problem where you're doing a truss, truss analysis. I'm sure you all have seen truss analysis before, maybe in statics. You might have done some simple ones. But you're bookkeeping all your forces and vectors and equations, and then there's these numbers. When I'm grading your exam, there's these numbers that are just showing up out of nowhere. I'm like, where are they getting these numbers? It's because in exam mode, when you get into that mindset, you're doing the exam, you took some numbers from your formula sheet and put them in your truss analysis, and now nothing makes any sense, okay? I say I don't want any worked out examples on the formula sheet, not for my sake, but for yours, because I don't want you to have the tendency to start pulling numbers from an example problem and throwing them on the exam. It can drive you nuts, okay? So yeah, any questions about that? Okay. Just so you are aware, and this class is at 8 o'clock in the morning, so I thought this was worth mentioning. If you ever go to here's the example I use. You ever go to a Mexican restaurant, you look at the menu, and there's those items that have the chili pepper next to it. What does that mean? Spicy. Well, I think there should be something like that for classes in an engineering curriculum, only those are the courses that have calculus in them. So we are going to see some calculus in here. I want to prep you for that. This is going to be kind of like a physics class, kind of like a math class, kind of like a theory class. So there's going to be some geometry, some trig, some derivatives, some integrals, but it's not terribly, terribly challenging stuff. Like I'm never going to ask you to take the integral of the sine of x to the 4th times e to the tangent of x from 0 to negative pi over 3. Like I'm not doing that. It's pretty basic, straightforward stuff, but it's going to be there. So I just wanted you to be prepared for that. So when it's 8 o'clock in the morning and you forgot your coffee and I throw an integral, you're like, oh no, it's too early. I can't do this. Any questions so far? All right. Okay. Let me pull up the syllabus because there's a couple things I do want to point out on it. Okay. Once it decides to load. Okay. All right. Couple things. All right. So first off, when it comes to the grades, I round. Okay. So if we calculate your class average, your composite grade, and it comes out to an 89.7, you got an A. Okay. So I round. And I say that because Blackboard doesn't, okay, because I have a column in Blackboard that'll calculate your class average, and if it calculates it to an 89.783, it'll say B+. So if that happens, well, hey, Dr. Mike said you're getting an A. Don't worry, okay? So I round up to the nearest decimal point. Now, if you have an 89.1, well, that's an 89 and that's a B, okay? So, but I do round up, okay? I'm usually pretty easy to get along with, and there is an opportunity at the end for some for a couple bonus points, and I'll mention that when we get near the end of the semester. Let's see. I'm going to skip, like a lot of this I've already talked about, like the homework policy and attendance policy and whatnot. I'm going to skip over all of that. I do want to bring up this. This is the last page in the syllabus. This is our tentative schedule for the semester. So a couple things that are worth pointing out. So over there on the right is when assignments will be assigned and when they're due. And, you know, at the very least, you're given a week in between assignments. In most cases, you're given more than a week. It's usually like a week and a half, and I think even one instance it's like 2 weeks because that assignment's particularly big. So I want you to know that there's you've got plenty of time to do the assignments. There are 8 homework assignments that are going to happen in the class. I mentioned instructional analysis. There may be 9 in here. It's pretty much going to be locked in at 8. The exam dates that I have in here are fairly set in stone. They're probably not going to change very much. I mean, they might get shifted around a day or two, but not very much. I do want to point out, though, what's going on with exam dates in terms of review. So if you look at exam 1, so I have exam 1 scheduled for Tuesday, September 25th, okay? The date or the lecture before that, which is Thursday, September 20th, we're going to have an exam review session. So what's going to happen is I'm going to come in here and I'm going to go, you know, maybe for about 5 minutes talking about what is going to kind of be on the exam. I'm not going to tell you what the answer to number 2 is or anything like that, but I'm going to tell you, okay, here's the format of the exam, here's what to expect, here's the homework it'll cover, the lectures it'll cover. I'll talk about, you know, the topics you should discuss. I'll do that for about 5 or 10 minutes, and then I'm going to sit here and I'm going to shut up and I'm going to let you all ask whatever you want, whatever questions you want. If you want to talk about, well, how did you get the answer to number 4 on homework 2? Like, we can go over that. We can talk about if you didn't understand what was on slide 36, we can talk about that. If you want to talk about an example problem that we did. It's basically your opportunity to ask whatever you want about anything pertaining to that exam, okay? So I want you to be aware that I'm going to give you that opportunity. But at the same token, I don't want to come in here and I'm like, okay, do y'all have any questions? And you all didn't like look at things ahead of time and it's, you know, crickets. You know, so make sure that you're prepared to ask those questions as that comes around. Another thing worth mentioning, so I have, if you notice here in the schedule, I have these makeup days. And that's for a couple reasons. One, we can have a tendency, like, I like these courses to be pretty organic. Like, I'm not doing this for my sake, I'm doing it for yours. So I really want you to feel that if you've got a question, if there's something you don't understand, I want you to ask it. So I throw some makeup days in there because we may fall behind because, you know, there's some questions you all had, or we might be ahead, okay? So I like to have a buffer in there. And if for some reason we're ahead of schedule and we don't need to meet, well, we won't. So for instance, I have a makeup day scheduled right before Thanksgiving break. If we're on schedule and we're rocking and rolling and you all are good, we'll just call it, okay? So I want you to be aware of that. Second, and this is why I want to point out the absolute most important word on this schedule right here, and that's this word tentative, okay? Just so you're aware, so my wife is currently pregnant with our first child, and she is due in October, right in the middle of the semester. So when middle of October runs around, and I got these dark circles under my eyes that are even worse than I'm having right now because of the 8 o'clock class and what have you. And if I need to adjust the schedule around a little bit because of that, I just ask that you bear with me, just be patient with me. I'll make sure and look out for you. But I've got some buffers there in the schedule for that. Everybody good? All right. Before we dig into the actual concepts of the class and get into it, let's talk about Blackboard because I wanted to throw that out there. So I'm here on the Blackboard page. This is the page for the class. I've got it in student view, so this is what you should see when you log in. So first off, I've got the syllabus there where it says YouTube playlist. If you click that link, it'll take you straight to the YouTube playlist. Now, it's empty. because there's no videos on it, but that's where that will take you right there. So if I click that, bam. So there'll be videos as the course progresses. The way it works, the software that I use, it'll record the video, it'll process it, and it'll upload it to video or to YouTube. I have to actually take the video and add it to the playlist. So I'll usually try and do that like by the end of business that day, but I'm usually pretty up to date on that. But if for some reason I forget, if it's not on the playlist, it's on my YouTube channel, so it's pretty easy to find. Lecture notes. This is everything for the class, period, okay? So I have every set of lecture notes for the entire course, so everything's there. I used to upload them like as the semester progressed, but I said, you know what? A, it's going to be a really hectic semester for me as October rolls around, and B, I've got a lot of this stuff prepped. Let's just give it to y'all at once. So this is everything. This is every lecture note for this class, so this is all the slides from the PowerPoints. Also, I've got some supplement files. I might add a couple here and there, but by and large, this is what I'll use. I've also got the exam review slides. They're there as well, so everything is here. Also, if you go to grades, I've already got the grades set up. Now, there's no homework assignments here. As the semester progresses, I will add those. But you'll be able to see all of your grades in real time. And I know what will happen when it gets to late November and the finals rolling around. You all will start playing the at-home game, where you start looking at the grades like, okay, what do I need to get on the final to get a B or to get a C? I know you all do that. So I want to make sure I've given you all of the ammunition to play the at-home game. So, sound good? Any questions? All right. Well, usually I don't like to get too heavy into lecture on the first day, but since we only meet 2 days a week, I feel like we need to take the time to actually start getting into things. So I actually do want to talk a little bit about the concept of mechanics and materials, but what I also kind of want to answer on the first day is why the heck you're even in this class. It's 8 o'clock in the morning. I'm sure, it's like, oh, I really have to be here. But my philosophy is this. Yes, I know Marshall told you that in order to get a degree in engineering, you had to take this class, but I want you to understand why, okay? I want you to understand why this class is important and how it's going to benefit you as an engineer. And I don't mean to be melodramatic when I say this, but whether you're a civil engineer or a mechanical engineer doesn't really matter. Mechanics of deformable bodies is one of the most important sciences you will learn as an engineer, period. And I think after what we do today, I think that will kind of click with you a little bit. Now, to get started, I want to introduce some scenarios. I just want to have a little bit of discussion and let's see what's going on here. Okay, so I've got this scenario here on the slide, but I want to bring a little bit of reality into it. Okay, so I've got here some images, and let's just have a discussion. Okay. So I've got some images here of some aluminum cans, some Coke cans, Sprite cans, what have you, okay? Now on this tab, I've got some images of some aluminum bars, okay? So let's take like this one, for instance, and let's take this one, just for the sake of discussion, okay? So let's say, for the sake of discussion, that these are made of the exact same material, okay? So it's the same aluminum alloy and everything, okay? Now, let me ask you this. If I have one of these two items, let's say, in my hands, is one of them going to be easier to fail or crush or destroy than the other? Is one of them going to be easier to fail? And let's say, for the sake of discussion, the can's empty. We're only talking about just the can. So everybody's sort of shaking their head yes, and they're saying the can, right? Now I'm going to ask you why. I mean, because now, I know it might sound silly, but they're both made of the same material. So why is it that the can's easier to fail than the bar? Hollow, but let's take it and make it even simpler. Like what? Just a simpler verb than just it being, or a simpler adjective than it just being hollow. It's smaller, right? Right? It's just a smaller object. So let's look at. Let's add some numbers to it, and let's do this. Okay, so let's say I have these two elements, and they're both made of the same material. Okay, Now, I like going to the lab and breaking things. My general philosophy is any day with controlled demolition is a good day. So let's say I take one of these bars, let's say the bar up top, and I yank on it. I start applying tension. Let's say I do it in a controlled environment, you know, with a hydraulic actuator so I can measure everything really accurately. And let's say with this material, doesn't really matter what it is, but at 100 pounds, snaps in half. Okay. Now, let's say I take that same 100 pounds and I put it on this bar. Do you think it's going to fail at 100 pounds? If this one failed at 100 pounds, do you think this one's going to fail at 100 pounds? No, right? This one's going to take a lot more, right? Because it's bigger, maybe 200 pounds, maybe 300 pounds, what have you, right? So would you agree that this one is going to be able to accept more load than this one? Fair point? Okay. So the reason is because of the section's geometry. It's bigger, so it can withstand more load. I got a feeling that everybody in here has probably been familiarized with the concept of pressure, right? You've probably heard of the concept of pressure before, right? You know, it's not how many pounds, it's how many pounds per square inch, or how, you know, how many kilonewtons per square meter, or what have you, depending upon what unit system you have. We don't really like to use the term pressure in this course, and we don't really like to use the term pressure. Like, we have to be careful when we use those terms. Pressure is a term that we as engineers reserve for fluids. So for like liquids and gases and water and stuff like that. Pressure is what we deal with when we deal with fluids. But for solids, when we have like, you know, bars and beams and columns and gears and stuff like that, when we have solid bodies that are subjected to loads, we don't like to use the term pressure, we like to use the term stress. So right off the bat, if you want to know generally what stress is, that's what we're talking about when it comes to stress. You know, on day one, you can think of stress and pressure interchangeably. You know, instead of force, it's force per unit area. You know, instead of pounds, it's, you know, pounds per square inch and what have you. But in the end, that's kind of what's going on. So to give you kind of an idea, let's say this failed at 100 pounds, and this rod, let's say this rod was 3 times bigger, right? So would it make sense that if it's 3 times bigger, it would fail at 300 pounds? Make sense? It's because when you look at this from a material perspective, materials, it doesn't really matter so much what the load is. What matters is what the stress is. So it's not that it's failing under the same load, it's failing under the same stress. So it's not that force, it's that force per unit area, okay? So that's really one of the first concepts that the course sort of tries to remove is the geometry. You know, if I understand how a material behaves, when it doesn't matter if that material is used to make an aluminum can or an aluminum bar or whatever, if I understand how aluminum behaves and I understand aluminum's limits, I can use aluminum in any design scenario, okay? Now that brings up the second scenario, okay? Now, I've got some numbers here just as well, but I want to give you another example. Okay, so let's look at this and let's look at this, okay? Now, let's say for the sake of discussion that these bolts are the exact same size, okay? So this scenario, I'm doing something a little different. I'm not dealing with an aluminum or a can and a bar where I've got elements that are different sizes. Now I'm taking the size, the geometry out of the equation, okay? Now let's say we're talking about this bolt here and this bolt. Let's say now that they are the exact same size. So now the geometry is the same. Which one do you think is going to fail first if I start applying load, the plastic bolt or the steel bolt? Plastic bolt, okay, and that's pretty common, okay? Why is that? Because in general, you would think that plastic is weaker than steel, right? Pretty straightforward, okay? So another thing that we have to deal with in this course is how we characterize material behavior. Not just the geometry, but the material. So let's go back to that scenario. Let's say I've got that rod of that, let's say, blue material or what have you, and I load it until it hits 100 pounds and it snaps in half. Well, what about the lower rod? Is it going to fail at 100 pounds? Is it going to be higher or lower? Well, it depends. Is this plastic and this steel? Is it aluminum? Is it nylon? Is it what have you? It depends, okay? So the reason why it depends is because of the section's material properties. So material properties are going to affect how sections respond to load, and they're also going to affect how things fail. Like, for instance, if I have a bolt, and just for the sake of, let's say this bolt was made out of wood. Well, how would wood fail? Well, it would tend to like split, like the fibers would split and it'd split apart. If I had it was made out of an alloy like a steel, it might want to bend or fracture. If for some reason it was made out of like concrete, it would crack and what have you. So the way that that material behaves and that the associated properties with the material are really important in capturing behavior, okay? Now, another thing that's really going to occupy a lot of our time this semester is how are we loading it? What happens if instead of yanking on the rod, what happens if we bend it? What happens if we twist it? What happens if we shear it? Those different types of forces applied to those elements are going to cause different stresses, and they're going to fail in different ways, okay? So how elements respond to those stresses and how they respond to multiple stresses acting all at once is going to be a really significant component of this class. But I think, you see the eye on the prize after we do our first example here in a little bit. What I'll say about this, and this is something that we're going to investigate throughout the semester, so I don't want to get too marred into details and into minutia of the course, but what I'll say is this. The way that you load an element and the way that you apply force, if we're talking about a beam in a building or a camshaft in a car or what have you, the way in which an element is subjected to stress affects how it behaves and affects its performance. You wouldn't analyze a beam in a building the same way that you would a gear in a car. Okay? They experience different stresses and they experience them in a different fashion. Even if the material properties are very similar, the resulting stresses can be very different. And how we determine those stresses is going to be a big focus of this course. So that's something I do want to mention. And there's a couple other interesting points. The way a material behaves, and we'll talk about the difference between elastic behavior and plastic behavior. Suffice it to say that a lot of materials can behave elastically up until a certain point. Like imagine that Coke can. If I take that Coke can and just very lightly bend it, it has a tendency to want to pop back, right? But if I take it and crush it, it's not going back, right? It's stuck that way. So that's the difference between elastic and plastic behavior. Load orientation. It's like imagine if you have a yardstick. You can take that yardstick and you can yank on it all day long, but as soon as you take that yardstick and push it, it fails after a few pounds. That's because the yardstick wants to buckle. And so buckling is a concept that we'll deal with near the end of the semester. Things like what is stiffness and how does member orientation matter? How do you handle multiple stresses? This is going to be something that we deal with throughout the semester. So before we get into some nitty-gritty details with the math and get into some examples, anybody have any questions? Okay. Like I said, after today's lecture, I think you will definitely see where this is going as an engineer. Let's try and get some more formal definitions of stress and get into some actual math and some examples. Okay? So like I said, stresses are going to be a big topic of discussion in this class. Okay? So one way of thinking about stresses is stresses are a way that a body, and when I say body, it could be a beam, it could be a column, it could be a gear, it could be whatever. Stresses are one of the ways that a body deals with external loads being applied to it. You put force on a beam, on a column, or what have you, it responds by developing stresses inside. So I'm sure you all have seen a problem like this before in statics, okay? And don't get me wrong, we are going to use some statics in this class, and I know sometimes you can hear that word and begins the onset of acute post-traumatic stress disorder, but don't worry, it's not going to be that bad. We're not going to see any IJK or any vectors or anything like that in this class, but we are going to use some very, very basic principles in statics to get behind our points. Now, here's a beam subjected to some loads. One of the secret weapons of engineering is a samurai sword or a lightsaber if you happen to be a sci-fi fan. Okay, so here's what I mean by that. Let's say I've got this table right here, and I'm sitting on the table, so I'm this distributed force applying force to the table, right? So So if I'm sitting on the table, there's obviously going to be support reactions here, etc., right? Okay. Now let's say he doesn't like me very much, and he has a samurai sword or lightsaber, because again, it's the secret weapon of being an engineer. And here's the table from here to here, and he cuts through the table right here, okay? What's happening to me? I'm going down, right? What's happening to his grade? I'm just kidding. But seriously though, if you cut this beam at this particular point, the beam is going to collapse, okay? The reason why is because at this particular point, there are forces inside that are being developed, forces that are meant to resist that load, right? That's how the beam responds. Now, if you've got three equations of equilibrium, you know, sum of forces in the x direction, sum of forces in the y direction, and sum of moments, then you've got three potential forces that can be inside that beam. And how those forces generate stresses is going to be a big part of this class, so I'll leave it at that. But suffice it to say that for our purposes here, we could develop a force in the x direction, which is acting along the axis of the member. So we call that an axial load. That's what that term P is. We can develop a bending moment, you know, bending that section, and we can develop a shearing force. And remember, you know, and this is a principle from statics you might remember, if you cut a section on either side, you get equal and opposite members, right? So if he's got a rope and I've got the other end of the rope and we're playing tug of war, we might be pulling on it with 20 pounds of tension or what have you, but we're acting in opposite directions. He's pulling that way, I'm pulling this way. We're doing the same thing to the rope, but in opposite directions, right? Everybody's okay with that? That should be a concept you're somewhat familiar with. Now, that's in 2 dimensions. If we were getting fancy and doing 3 dimensions, you know, we'd have 3 forces and 3 moments. I'm not going to like go nuts into the 3D stuff with this course. Honestly, as engineers, you know, if you were to ask me, just if you were in high school and you were asking me, like you didn't know anything about engineering, and you asked me, how do engineers deal with 3D stuff? My answer would be, we try and deal with it in 2 dimensions as much as possible, okay? And by and large, engineers do that. Two dimensions is a little easier to analyze, and there's a little more surety of the results. But we can deal with things, we can see things in 3 dimensions. I think the real big thing that is worth mentioning though for us in 3 dimensions is, you know, you can have 3 forces and 3 moments. The moment that acts along the axis of the member is acting to twist that member, okay? And so we have a particular name for that in this course. We call that torsion. And so how we deal with torsion is going to be a big component of the course to come. Now, I think after the first couple scenarios, you know, ultimately, we really don't care so much about forces as we care about stresses, okay? So if I want to be a little bit of a mathematical purist, okay, so you probably remember this from calculus. You start developing the concept of integrals and derivatives and whatnot. You remember that concept of dx, right? So, you know, you've got a curve, some function of x, and you're trying to determine what's that value of really, you know, infinitesimal narrow strip, that differential element, that dx. We tend to refer to that a lot in here because the idea is if we can determine you know, the forces and the stresses on that little differential element, we can integrate that over the member and determine the response overall. So we will see some of that response or that terminology throughout the course. But suffice it to say, you know, if I cut a section, you know, if I've got this member and I cut a section, I can have all sorts of different forces and moments acting in all sorts of different directions. But if I'm trying to determine a definition for stress, if I look at that little itty-bitty differential element, that little tiny element, and try and look at what's going on with that element, because it's so small and it's so infinitesimal, I can say, for our purposes of analysis, there's really only 2 forces I need to consider myself, or I need to consider. A normal force, remember normal acting normal to the plane, and then a shearing stress, or a normal force and a shearing force. So the big difference between the two is normal being, you know, sort of normal to the plane, and shearing, I'm talking about parallel to the plane. So for those forces, again, I don't really care so much about forces, I care about stresses. So a pure mathematical definition of stress would be, well, for normal stress, it'd be that normal force over the area, and then what is that that division as the area gets smaller and smaller. That's what we're talking about when it comes to a normal stress. For normal, we're talking about the normal force. For shearing stress, we're talking about the parallel force. Now, a couple things on units. So in this course, I'm going to do my best to expose you to both unit systems. The reason why, look, don't get me wrong, I know I'm an engineer and I'm an American, but I'm a scientist, and don't get me wrong, I understand that the SI system makes the most sense, from a computational standpoint. I get that, and you don't have to convince me of that. We have civil engineers and mechanical engineers in this room, and whether or not you're working with mechanics or whether or not you're working with construction companies or what have you, we use U.S. units in this country, okay? It's a fact. Go to a contractor in America and tell him that you need so many cubic meters of fill. He's going to say, what? Yeah, I'm sorry, it's just the facts. A lot of our specifications are written in American units, and that can apply to civils and mechanicals as well. So I am going to expose you to both. And plus, it's going to be on the FE exam and what have you, so I just think it's a wise decision. A couple things. So I believe you all have probably seen or heard of a kip before. Have you heard that? Okay, so a kip is 1,000 pounds. So we'll see stress units in PSI and in KSI. So KSI is 1,000 PSI, so hopefully you're okay with that. And then in units, we'll be dealing for SI, for units, we'll be dealing in pascals. So Newton per meter squared, that's a pascal. And a quick shortcut, if you have a kilonewton per a millimeter squared, that's a gigapascal. So I just write that down because it's nice to remember that one. Now, traditional, and if we're getting technical with our theoretical or mathematical definitions, stress is a limit. But for practical applications, more often than not, and as an engineer, you're just going to be looking at average stresses, just force over area. And we'll talk about later why that's valid. But for the sake of our discussion, I will pretty much never ask you to actually perform the limit evaluation. It's just going to be P over A or similar formulas. So you can relax with that. We're not going to get into limits on day one. But we will see some calculus here and there. Okay. In order to really, really evaluate what's going on with stresses and really sort of understand it, and also to get your memories and get your minds jogged and get you geared up, ready for some of the stuff that we're going to do in this class, I got an example for us. Okay, so let's take a look at this example. Okay, I want to determine the stress in each of these members if the area is 4.5 square inches. Okay, and we're going to express it in terms of KSI, and that'll be a actually simple approach. But this is going to be a little bit of a statics review and a little bit of just get us back into the swing of things. Okay. All right. So now let's see how my software works on day one. All right. So can you all read that? That big enough? Okay. All right. So I've got this truss. I'm going to redraw it up here. We're going to determine some support reactions. We're going to do some basic truss analysis. Now I'm going to do things a little differently than probably what you're expecting in statics, and the way I present it's going to be a little different, but I think it'll be a little easier to follow. So let's see. Here's my truss. And if you don't have the notes, don't worry. I'm going to reproduce the dimensions and whatnot for you. It's no big deal. So that's a roller. That's a hinge. Okay, and I've got 50 kips, and I've got 20 kips. Okay, this is A, this is B, this is C. Okay, for dimensions, I've got this right here. Is 15 feet. All right. This one here is split into two. This is 15 feet. This is 35 feet. Okay. Sound good? Now let's pop quiz you a little bit. So if I have a truss analysis, this is the problem I give you. What do you think the first step into performing this truss analysis is? Before you do anything, like you remember there's method of joints and method of sections. I know it's been a while, right? But what's the first thing that we need? To find the reactions. There we go. Now, in order to find the reactions, okay, what we're going to need to do is start assuming some directions. Now, before that, let's take it one step at a time. Okay, so let's look at C. C is a roller. So how many reactions are we going to have at the roller? One, and it's a vertical reaction, right? So I'm just going to draw a line right here, and we'll call that CY, okay? Again, no vectors, no IJK, none of that stuff, okay? Now, that hinge over there, that pin over there on A, there's how many reactions? Two, right? A horizontal and a vertical, right? Okay. Now, okay. So we'll call that AY and AX, okay? Now, in order to perform this analysis, we need to make some assumptions, okay? So let's start off with AX, okay? AX is a horizontal reaction. You tell me, do you think that AX is acting to the right or do you think it's acting to the left? To the left, okay? Now, what about AY and CY? What do you think is a good assumption for them? Up or down? Up. Okay. I like to draw a little line through my reactions to indicate those are the ones that are unknown. Apologies if the lines are a little sloppy on the diagram. Sometimes it's a little difficult on this. I try and keep it somewhat neat. Now, we guessed that these reactions are going up and to the left, okay? If our guesses are incorrect, it does not mean we need to develop significant emotional distress. It just means that we're going to get a negative answer, and so if we guess up, that means it's going down. That's all that means. So again, it's just a guess. It's just an assumption. Assumptions are fine as long as you verify them. Now, let's keep this simple. Okay, we have two unknown reactions in the vertical direction. We have one unknown reaction in the horizontal direction. What's the easiest one to solve for? The horizontal, right? And so in order to solve for that horizontal reaction, I'm going to utilize that the sum of forces in the x direction equals 0. But look, I'm an engineer. Let's just keep it simple. What is AX? All right, there we go. AX is 50 kips. And I write kip sometimes with just a little k, just, you know, sort of up like that. And it's acting to the left, right? It's that simple. Let's just move on there. Now, we've got two forces, two unknown forces in the y direction. So we have some forces in the y direction. We have sum of moments. Okay. Now, if you remember, you can be a little strategic with sum of moments. In other words, if you sum moments where you got a lot of forces together, you can eliminate a lot of them. Okay. So how about this? Why don't we sum moments here at A? Because we don't have any moment from this and we don't have any moment from that. Y'all remember this? It's been a while, right? Okay. All right, so let's sum moments at A. Now, the way that I sum moments is a little different, okay? So I'll prepare you for that. When you sum moments, and the easiest way, let's talk about forces. Let's say we're summing forces in the y direction. You say that sum of forces in the y direction is equal to 0, but another way of saying that is everything going up's got to equal everything going down, right? That's what that means, right? So what I'm going to do is this for sum of moments. I'm going to draw myself a little table, okay? I'm going to draw myself a little table about like this, and I'm going to put all of my moments going this way and all of my moments going this way on opposite sides. And then I'll just sum them up and solve. And I think you'll find this pretty straightforward. Okay. The way I like to do this is I just keep my finger at A and I take one force one at a time. So let's start at A. AX, does AX generate any moment at A? It's going right through it, right? Now, it's been a while, but this is bringing back memories, right? What about AY? Okay. What about the 50 kips? This one right here, is that causing moment? Okay, all right. So 50 kips, if I'm at A, is doing this, right? So does it belong on the left side of the table or the right side of the table? Left side. Now, how far is that from A? 15 feet. Bringing it back, right? So what I do is over here, I put 50 kips and 15 feet. It's that simple. What about the 20 kips? Is that causing moment? What side of the table does it belong on, left or right? The left, right? And from A, how far is that 20 kips? 15. So we have 20 times 15. Okay? Now, what about the CY? Does the CY cause moment? What direction? What should belong on the left? The right side, because it's doing that. How far is it from A? 50 feet, right? So, CY, 50 feet. And that's it. Just draw a line. And then, for the math, this is what we do. Anybody tell me, what is 50 times 15? Okay, so that's 750. What's 20 times 15? 300, right? So if I add those up, what do I get? I get 1050, and that's foot kips. And that equals CY times 50 feet. So how do I determine CY? Divide by 50. So has everybody got a calculator on them? By the way, 21. It's 21. Just as a piece of advice, I would bring a calculator because we are going to be doing a lot of examples together. And I mean, like, I've got the answer. You know, it's not for me. It's so that you can do the example along with me. So I would bring one. So CY, so if I divide both sides by 50, CY is 21, right? Now, did that answer come out as positive or negative? Like, if I solve this for CY, is it going to be a positive 21 or a negative 21? Positive, right? So that means that my assumption was correct, and it's 21 kips acting upwards. Pretty straightforward, right? Okay, now, we got one other equation left, and what's that? Sum of forces in the y direction, right? So let's do that. So the way that I do that, I say, all right, let's sum forces in the y direction. Draw us a similar table. I'll put everything going up over here, everything going down over here. Okay? And then we start just listing them out one at a time. Do I put this there, the AX? It's not a vertical force, so no. What about the AY? What side do I put it on? Left side. Do I know what it is? No, I haven't figured it out yet. So this is AY. What about the 50 kips? Do I put the 50 kips? What about the 20 kips? Put that on the right side. Far cry from IJK, isn't it? All right. What about the CY? Do I put that on there? What side do I put it on? Left. And so the way I like to do that, I like to say CY is 21 kips. And I put it over there because I know it's acting upwards. So sum it up. So I got AY plus 21 kips equals 20 kips. So what's AY? Negative 1 kips. So if I get a negative answer, it does not mean I need to develop significant emotional distress. It just means I've got 1 kip going down. I assumed AY was going up, and I was wrong. That's all that means. Sound good? So to summarize your reactions, AX is 50 kips to the left. AY is 1 kip going down. CY is 21 kips going up. Not too bad, right? Pretty straightforward. Any questions? Okay. Now, we can break out method of joints or method of sections. Personally, I think method of joints is a little easier, so I'm going to do that. Before I do method of joints, I want to look at something. Let's go back to this truss. I want to look at member AB, this one right here. If I go from point A to point B, how far over do I go? And how far up do I go? 15. So would it be fair to say that this is 45 degrees or a 1-to-1? Now, you said 45 degrees. I do want to make a point. I actually don't like to use much trig in truss analysis because I think it ultimately just adds computations. Because what a lot of people do is they'll say, all right, I need to figure out that angle so I can take the sine and cosine of that angle to figure out the components. But all you're doing is making one big runaround around SOHCAHTOA, right? Just use SOHCAHTOA to determine your x and y components. You don't have to worry about it. And I'll show you how here in a second. It ends up being a lot easier. Now, from B to C, you go over 35 and up 15, right? So 35 over 15 is what? 7/3? Is that right? So can I simplify this by saying 3 to 7? Everybody okay with that? You're going to see how I'm going to use that here in a second. Everybody okay with this? Any questions? All right. So if you have everything over here, I'm going to go on over to the next sheet. So I'm just going to hit the next page. By the way, I save this notebook as one big file. So like on our exam days, we can go back to what we saw. Like what'd you do on example 4? So I will save all of these. Okay. So okay. All right. Now, let's look at joint A. So let's look at the method of joints. Let's look at joint A. Let's see what we got going on with joint A. So if you recall, we've got, it's a joint that looks something about like this, right? Where that member is at a 1-to-1. Okay? Now, we have some reactions. We've got, let's see, we have a 50 kip reaction going this way. We have a 1 kip reaction going this way, right? Now, the way I like to do this, the way I like to split this up is this. See this horizontal member? It's got one force. I like to call this force AC. Now this diagonal member, it obviously has one force as well, but I like to split it up into its components. So we've got ABX, we have ABY, okay? One other thing I like to do with all of these forces, I always like to assume that they're in tension. So if I'm wrong, I'll get a negative answer and I'll know they're in compression. So if you just automatically always assume tension positive, it's really easy to know what the answer is. It's either positive and it's in tension or it's negative and it's in compression. Just always assume tension. It's a lot easier. Now, let's take a look at this. How many unknown horizontal forces do we have? Horizontal. How many unknown verticals? 1. Okay, so we're engineers. Let's just keep this simple. If we sum forces in the y direction, what is ABY? 1 kip. Is it acting upward? It is acting upward. Okay? Now, ABY and ABX are related, right? They are related by that slope ratio, this right here. It's a 1-to-1, right? What that means is that whatever ABY is, ABX is the same thing. If it was 1 to 2, it'd be half of it or double of it or what have you. So if we know that ABY is 1 because of that slope ratio, we know that's the case as well. Sound good? Now, can anybody tell me what AC is? Because we're going to sum forces in the x direction. Anybody tell me what that is? What do you think? What do we have going in the x direction? We have 50 going this way, right? 49, right? Everybody see that? 50 going to the left. This is only 1 to the right. We need another 49 to the right to meet equilibrium. So AC (49 to the right). Is everybody okay with that? Now, I'm lazy. When we look at the remainder of our truss, let me go back a slide. I can solve joint B complexity leads to less errors. So here's joint C. What did we have? We had a (21 kip) force there. Do we know any of the forces going into this? By the way, I need to put that slope ratio on there. That's 3 and that's 7. Do we know any of these forces? Like, do we know what's going on this member? It's AC, right? And so AC was 49 kips. So we know that this is 49 kips. Now, should that 49 kips be pointed to the left or pointed to the right? To the left. Tug of war, right? Look at AC over here. It's going this way. Again, tug of war. If he's got a rope and I got a rope and we're yanking on it, we're both putting 49,000 pounds on it because we're pretty built, but we're pulling on it in opposite directions. All right? So this is 49 kips going this way. Our unknowns are this and this, right? Now, like I said, if you don't know, assume. But let me ask you this. Look at our unknowns. Okay, so this is BCX and BCY. What direction do you think BCX is going to go? There we go. What about BCY? Sound good? Now, if I solve for each of those, what do you think I'm going to get? It's pretty straightforward, right? 2149, right? So, therefore, BCX is 49 kips to the right, BCY 21 kips down. Does anybody have a calculator with them? What is 49 divided by 21? Just as a decimal, just what do you get? 2.3 repeating. Now what's 7 divided by 3? There's your check. These two forces are related. They're related by this slope ratio. So that's a check to see if your analysis is correct. All right? Does that make sense? So to summarize our truss analysis, okay, so to summarize, okay, we know that, so we have three members, AB, AC, and BC. Now we know AC, that one's pretty simple. That's 49 kips. And that, now, remind me, is that in tension or compression? It's in tension, right? Remember, AC is yanking away from the joint, right? Now, let's handle some simple stuff. Let's start off with AB. Is AB going to be in tension or compression? Tension. It's yanking away from the joint, right? Now, how do we determine what AB is? If we have ABX and ABY, how do we determine what AB is? Pythagorean theorem, right? So what's the square root of that squared plus that squared? So I'll write that out. Square root of 2, or it's like 1.41, right? So square root of 1 kip squared plus 1 kip squared. And so that's 1.41 kips, and that's in tension, right? BC. Is BC going to be in tension or compression? It's pushing towards the joint, right? Here's the joint, and they're both going towards it, right? So what is the square root of, what, 49 squared plus 21 squared? So we got... What do we got here? We'll say 2 decimal places. Anybody got anything? 53.31 kips. I usually like to ask for a second, like if anybody else got it. Got a second? There we go. I do that quite a bit, so if you hear me say anybody got a second, that's what I'm talking about. So, everybody okay with this? Now that's a review. Everybody, it's not that it's been a while, but with enough study, enough time, you can figure that out, okay? Here's the new stuff. Here's the new stuff. If you recall, let's talk about stresses. If you recall, for all these members, the area was 4.5 square inches, right? Remember, it's not the force, right? It's not 100 pounds. It's how many pounds per square inch, right? Or how many kips per square inch, okay? So what I'm going to do is this. I'm going to take each of these forces, and I'm going to divide them by 4.5 because I want to determine the stress, okay? I want to determine the stress. And so we're going to have a discussion about that, and I think you'll see where this is all going. So let's look at the stress in AB. So that's going to be the force in AB divided by the area. So that's 1.41 kips divided by 4.5 square inches. What is that? We'll say 3 decimal places just for the sake of discussion. .313. Now, what are the units? Kips per inch squared, or KSI, right? Now, that's in tension. I'll go ahead and put that in tension. Do I have a second on that? All right. So, likewise, does anybody have AC and BC? Anybody tell me what we got here? So 10 point, I got like 889. I got a second on that? Is that what we got? And what about this one? Somebody else. $11.85, something like 847, something like that. Okay. Is everybody okay with this? Okay. So what I'm getting at is these are not the forces in those members. These are the stresses in those members. Okay? There's a point that I want to make about that. Remember, this area equals 4.5 square inches. Here's what that means. I've got that truss member, right? I take my samurai sword or my lightsaber and I cut through that member. That's how big that member is, 4.5 square inches of material, okay? Now, here's what wasn't in the example, and here's what I want you to think about. This is what I want to have a little discussion about before we leave. Let's talk about that. Let's say that these three truss members are made of aluminum, whatever. And this material, this aluminum material, at 11 KSI, it will fail. Talk to me. Tell me what you think about that. Tell me about these truss members. Tell me what you would do if you were the engineer. Let's talk about member AB. What can you tell me about member AB if this is the case? As an engineer, as the person, what's that? That's one way of looking at it. What's another way of looking at it? It's too big. You could make it smaller, right? Why waste money, right? You're the engineer. You're the person speccing this out. You're the person telling the contractor, or the mechanic, or whoever, make this truss out of this member. And if you get that result, that member's too big. See what I mean? This is what I'm talking about. Okay, let's talk about member BC. What's going on with BC? It's going to fail. We're going to talk about that here in a second. It's going to fail, right? So member BC is not big enough. So two solutions. You sort of reference either making it bigger, or you said it needs to be made out of something else, okay? Those are two potential options, and as engineers, you need to consider that. What if this truss, what if you only have so much room to put that truss in? And so you don't have any room to make it bigger. Maybe you got to go with what he said and use a different material, okay? Now, let's just look at the raw numbers by themselves. What can you say about member B or member AC? It's good, but it's close, right? And so you're broaching on a topic which is going to envelop the rest of your engineering careers, and that's the concept of a factor of safety. In other words, this material will fail at 11 KSI. In other words, if I go down to the lab and I load this material until it fails, it will fail at 11 KSI. Do I actually use 11 KSI in my calculations? Maybe I do, maybe I don't. It depends on the allowable factor of safety. It's like if you go to Walmart and you buy one of those, pieces of furniture, the desks or the, end tables that you can put together with the particle board, and it says something like, don't put more than 200 pounds on it or it'll fail. Well, really, probably what happens is it'll probably really fail at 400 pounds. But the manufacturer said, no. We're not going to tell people they can put 400 pounds on it and then it fails and we get a bunch of lawsuits. What they said is we're going to use a factor of safety of something like 2. If it really will fail at 400 pounds, we're going to tell people you can only put 200 pounds on it, okay? So what is the appropriate factor of safety? Is that factor of safety built into this? We'll talk about notations, difference between sigma allowable and sigma nominal, and how you as engineers should handle that. But if you want a reason why you're in this class, a reason why this science is important, that's why, okay? Because the concept of stresses is how you as engineers will design, period. That's all I've got. I will see you on Thursday. If you haven't had coffee and you drink coffee, get some. Y'all have a wonderful rest of your day. And I need the attendance sheet.